All right, so for a relation to be a function, every input has one output. So to make sure we're on the same page, basically what we're looking for is no duplicates. And so here we have an issue because 3 has an output of 4, but then it also has an output of 16. So this cannot be a function. Now here 3 goes to 4 and 10 goes to 4. Even though that's not unique output, it's just not a one-to-one function, this would be considered a function here. And then this one, 3 goes to 4, -5 goes to 7, 10 goes to -2, 12 goes to 1.5. That's a one-to-one function because none of the outputs repeat. So we're going to be talking about inverses. So if f and g are inverse functions, then g of x equals f inverse of x. It looks like f to the -1, but we read this as f inverse of x. And if xy is a point on the graph of f, then if you switch the coordinates, y comma x is a point on the graph of g of x. With inverse functions, all of the x and y values are switched, so the graphical behaviors in terms of x and y will be switched. So the domain of f becomes the range of f inverse of x, and the range of f becomes the domain of f inverse of x. All right, so the original table right here is or is not a function. Well, let's see. 1 goes to -1, 3 goes to 2, 4 goes to 0, but 6 also goes to 2. Now, even though the outputs repeat, the inputs are different, so that's okay. So the original table is a function because each input has exactly one output. Okay. When we do the inverse and we flip x and y, so -1, 1, 2, 3, 0, 4, 2, 6. The problem is that the inverse is not a function because 2 goes to 3 or 2 goes to 6. So one input has two different outputs. So graphically here, if we have the point -2, -1, -1, 2, 2, 1, and 4, 3, the inverse will flip that. So -1, -2, 2, -1, 2, 1 here becomes 1, 2. And then 4, 3 changes to 3, 4. So I just switched the x and y's. Okay. And if you did your inverse correctly, it's going to be perfectly symmetrical over the line y equals x. Which is true here. So the graphs of inverses are reflections over the line y equals x. All right, so the last thing is finding the inverse from an equation or function here. So if f of x equals 3x minus 7, the first thing you're going to do is want to rewrite it as y equals 3x minus 7. With inverses, we switch x and y, so x equals 3y minus 7. And now you just want to get y by itself. So I'm going to add 7 to both sides, and then divide by 3. And then we're just going to rewrite this as f inverse of x equals x plus 7 over 3. Okay. All right, so we'll do 2 more together here, and then the rest you should be able to try on your own. So again, we replace y with, we replace f of x with y. And because we're finding the inverse, we're going to flip x and y. So x equals y minus 2 over y plus 3. And this one's a little bit tougher. It's irrational. So to get y by itself, well, we have y in the numerator and y in the denominator. The first thing I'm going to do is multiply both sides by y plus 3. So I have x times the quantity y plus 3 equals y minus 2. Okay. And we have to get y alone on one side. So this is going to take a little bit of effort, but I'm going to distribute the x here. So xy plus 3x equals y minus 2. Okay. And if I subtract y from both sides and subtract 3x from both sides, I get xy minus y equals negative 3x minus 2. So at least the y's are together on the left side here, but I need to get it by itself. Now I can factor out the y as like the GCF. And then dividing both sides by x minus 1. We get y equals negative 3x minus 2 over x minus 1. And we'll just rewrite that as f inverse of x. All right, and last one together here for g of x. So just like we've been doing, we're going to replace g of x with y. We'll switch x and y. Okay. And now we want to get y by itself. So to get rid of the square root, I'm going to square both sides. And squaring a square root, those undo each other. Okay. I'll add 5 to both sides. And then lastly, I'll divide by 2. And then replace y with g inverse of x. All right, so try the rest of this worksheet and have a good rest of your day.